Welcome back. We made it to the beginning of the last lecture. Let's see if we can make it to the end. All right, so as usual, I tried to put up a summary of what we were discussing just before we finished last time. And I tried to generalize it a little bit compared to what I was showing, just to make some points to you in part convince you that I haven't missed something obvious. All right, so the general idea in A hydro, there are a couple of different ways to go about this, but the way I followed the most was the following. So you can, instead of assuming that you have an equilibrium distribution function plus some other thing, you deform the argument of the distribution function in this way, in a way that guarantees that at leading order this thing is always positive. Now, of course, in life, it's not every distribution function in the world is some stretched or squeezed distorted equilibrium distribution function. So in practice, you have to add a second order term, just like you do in normal viscous hydrodynamics. And we call that delta F tilde. There's a very long paper about how you do that and how it improves things. And in that long paper, it shows you that this thing always remains super small, even in free streaming, because this actually, in the free streaming limit, this will give you the exact result if you start with an equilibrium distribution function, and this thing remains small always. So it's just a different way of organizing the expansion. Instead of around a sphere, around an ellipse, because we already saw that naturally the thing has an elliptical deformation. So we're going to use that as our zeroth order approximation. But for what I'm going to show you today, I'm going to ignore delta F tilde, because if you go and look at 1311.620, you're going to see that it's another couple of weeks of lecture. This tensor that's sitting up here, Qc mu nu, in general, you can decompose it into the following bits. In equilibrium, it would simply be u nu, in which this would just be a nice equilibrium distribution function sitting here. As a function of the energy over some scale, which we would then identify as the temperature. And then out of equilibrium, we add two viscous hydrodynamics-like pieces. One is this anisotropy tensor, which we require to be traceless, and then another piece, which we're going to call the bulk in a hydro form, which is the same along the diagonals. And again, this is just a reshuffling of some general tensor that could be sitting here into a trace full and a traceless part. So there's nothing magical about this split. Now, in the case that you have a massless conformal gas, you can ignore this. So that's all I wrote down yesterday, because that's sort of what I had my eyes on. Good. Now, this tensor in general contains a bunch of components, and you have to derive equations for all of them, and we do that in practice. In the second part of today, I'll show you not all the gory details, but at least how it's all laid out for the phenomenology. But for today, I want to show you our friend conformal Bjorken again. And in the conformal Bjorken limit, ignoring this delta F tilde thing, we just have this spheroidally deformed, some people call it Ramachka-Strickland because that's where it came from in some paper, distribution function, where Qc is now encoding this anisotropy in momentum space. We finished, and I think you continued in the problem sessions, discussing how one of the magic things about this particular form is that you can factorize the length of P integrals and the angular integrals, and some special functions called R, and RT, and RL appear. I think Mubarak derived, at least, or showed you how you would get to RT and RL. And we went through how you get this function, at least up to the non-trivial angular integral, which you can just ask Mathematica these days, or maybe even ChatGPT. Good. So, what do we do next? Well, if we know these expressions here for the longitudinal and transverse pressures, we can immediately write down the following expression for our old friend, the shear viscous correction. the shear viscous correction is nothing but PEQ minus PL. If I rearrange this, I can bring PL over here to the other side. Pi is just, PL is just PEQ minus pi, and I've just done a little bit of the algebra quickly. So I can rewrite the standard viscous hydrodynamics shear correction in this way from its original definition. And in general, by energy momentum conservation, this energy density that's appearing here is always going to be, as we discussed last time, there's this kind of Landau matching criteria that at any time I can replace these two parameters, QC and lambda, by an equivalent temperature that has the same exact energy density. Something called the effective temperature. Anyway, I can rewrite this thing that's always going to be equal to EEQ by construction. So I can just replace it by EEQ. Where now this is just the same function up there. Maybe pi squared lambda to the 4 over 24. I don't know what it is, but it's the same function, just evaluated now at t instead of evaluated at lambda. Yeah. Good. And the second term, I'm just going to leave it generally written as I use them interchangeably. Now this one, we already know it's a conformal system, so that one's going to be a 1/3. And the second term is going, let's just do this step by step. So I can rewrite PL as RL of QC times PEQ of lambda. And in the bottom, I can write this as EEQ of lambda again. Sorry, yeah, that's right. R of QC times EEQ of lambda. Agreed? But once again, I know what this is here. It's conformal, even though it's not in equilibrium with a t sitting there, it still obeys this 1/3 relation. It's still 1/3. So then I can write this as 1/3 of 1 minus the ratio of these two special functions. Yes? Why is it energy density in equilibrium? Well, by construction, I'm always requiring that the energy density evaluated at the scale T is the energy density, the non-equilibrium energy density. It's Landau matching. I'm requiring that no matter what, this is how I define T, in fact. That's how I define T. You can take this as the definition of T. And here I've just used this in the first equation, but not the second equation because it turned out to be convenient for me to simplify it this way. Good. Now this tells us now, if you knew the spheroidal deformation parameter, what's the corresponding pi. And you can make a plot of this. So here I put log of 1 plus this deformation parameter QC, and I'm going to plot pi over epsilon. And my scale is not exactly right, just a second. plus 1/3. Now what I'm getting ready to draw is not obvious. You have to actually plug this into some sort of plotting routine and plot this thing. But it's completely bounded. And it goes between minus 2/3 when c goes to -1, which is this infinitely prolate limit, to c is 1/3 when c goes to infinity. Now what that means in practice is that already, remember that was this special number that we called the inverse Reynolds number, which was the square root pi mu nu. And people argue over the normalization. I like p here. This thing is just going to be proportional to the magnitude of p over the energy density. There's some proportionality constant floating around. But that's exactly what we plotted. So in this way, the starting point is that you'll never get an infinite Reynolds number out of this. It's sort of built in that it's bounded. The other thing that we're going to see in a little bit is that although this is a horribly nonlinear relationship, look at this function over here. It's got inverse tangents floating around. You can invert this numerically, or order by order in c, you can invert it, and then you can get c as a function of pi, and do it the other way around. And we're going to use that to sort of reverse the ahydro equations and cast them into viscous hydro form. So this is an important point. Bounded. Oh, I'm getting an echo over here. No echo. Good. All right, so now let's get the equations of motion. In conformal Bjorken hydro, conformal Bjorken ahydro. And we're going to use kinetic theory. That's the reason I was telling you so much about it. That one's beyond kinetic theory, but we derived it from kinetic theory. You know, it's energy, momentum, conservation. But the one that we did derive explicitly from kinetic theory was this one. And we're going to use these two equations of motion in order to obtain two ordinary differential equations for c and lambda. And c is sort of our stand-in for pi, and lambda is going to be sort of the stand-in for t. And they're both, in Bjorken hydro, they both depend on proper time. So this one, you won't be surprised to learn, reduces down to the same exact thing we had before, when written in a clever way. That's what we had before. Where pi over epsilon now in the new variables is this horrible thing in the box over here. But I want to write it in this form for foreshadowing reasons. Good. Now we get to use those special Cartesian basis vectors that I introduced last time. Remember, x0 through x3. And what we're going to do is start taking projections of this equation with the space-like vectors. So I'm going to take x nu I, x lambda I, d mu I mu nu lambda with I is equal to 1, 2, and 3. That's a lambda. Now, I is a label, it's not a Lorentz index, just a label for the basis vectors. So in this way, I mean, everything is fully contracted, so we're guaranteed that whatever equation we get out of here, Lorentz invariant. Yeah? Because I is just a label, it's not an index. Now, I'm not going to go through the next step. I can provide the reference that does so, or if you want to discuss it later. So you can take the I is equal to z, you can take I is equal to x and y. And the way the next equation is obtained is you take the equation that you obtain by projecting with zz here minus 1/3 of the equation you get by projecting with all of them equally. Now, the reason that you do this particular construction is to make it traceless. It's very much like what we did with the shear correction. Now, I'm doing this projection here on the left and the right, so let me write out the and you may ask why I'm only projecting with diagonal elements. That's because I'm Bjorken, I don't have any off-diagonal elements that I need to worry about. In general, there might be also off-diagonal terms and you need to worry about this and project with them, and then you get some more equations. But in this case, I really only need one equation out of this thing because I already have one equation, so I only need one equation out of here. And the way that to do that in a way that is going to guarantee that when I take the near equilibrium limit, which corresponds to Kc very, very small to 0, is that I do it in this way that, it's a traceless equation. So I take, this is equation in that sort of rough notation is that thing. I'll get three equations and then I combine them in this funny way. You do a little bit of algebra and you land, well, I should put a number before it goes away. Oh, I broke my favorite chalk. This was equation 1. And now we get equation 2, skipping some steps. Okay, that's it. It's very nonlinear. If you expand in Kc, this thing contains all orders in Kc going out to infinity, and I haven't truncated it. I just included exactly. Yeah? One of the nice things about doing this version of the equations is, as well as you can see, there's no time derivative of lambda appearing here. This is just directly gives you an update equation for Kc itself. In fact, this way of doing it guarantees that the time derivatives with respect to lambda just drop out automatically. Good, so in practice, what you would do is then throw these into your favorite ODE solver, be it mine would be Mathematica, and say solve it with some differential equations, and then you would get the solution. And you'll find in doing this, you'll never get any negative longitudinal pressures, et cetera, et cetera. It's all very well behaved, and if you take the free streaming limit, which means tau EQ goes to 0. It's not obvious from this way that it's, sorry, tau EQ goes to infinity. Sorry, then it is obvious. This term just goes away, and the remaining little ordinary differential equation that's sitting here, you can solve it, and it's the free streaming solution for the anisotropy, which, if I remember correctly, for Bjorken expansion corresponds to something like this in general. So tau EQ goes to infinity. This thing has a well-defined solution. This corresponds to the free streaming solution. And in that same limit, once you get this C, you can plug it up into the first one and you'll find the free streaming solution for the energy density, which is that instead of going like minus 4/3, it goes like minus 1. So the free streaming limit's built in here. It's non-trivial. What about small C limit? The next thing we had to prove was that, in fact, viscous hydro is contained, or second order viscous hydro is contained within these equations. So for that, I mentioned earlier that you can invert this relationship between C and pi over epsilon to rewrite, or plot if you like, C as a function of, sorry, I plot it in a slightly different way. So this is 1 over C. Now it's a function of pi. And I can plot it as a function of pi over epsilon. I'm going to put a little bar over here that means pi over epsilon, because it's a dimensionless number. And what you find, of course, this thing is a bounded function between minus 2/3 over here and 1/3 over there, just based on that plot. And you find something like that. Again, if I go over here, I'm going to the case that C is minus 1 and log of 0 is minus infinity. So that's shooting off to minus infinity. And over here at the other asymptote, it's shooting off to, that's not my phone, good. Shooting off to plus infinity. Now, of course, in this region, you can see that it's approximately linear. And if I want to go beyond the linear approximation, I can just systematically expand this function here and do the inversion that way. Clear? This corresponds to 0. Yeah, I meant to label it. Thank you. Thank you. And that corresponds to 0 here as well. Yes. So whenever pi is 0, C is 0. That's the reason there's always this 1 floating around in the formulas, is to make sure that this map is, I don't know, more beautiful. Some people remove the 1 and it upsets me. All right. Yeah.
Here we have this link between pi and C.
Yeah.
So this particular for Bjorken flow, because if you have more, if you have like particle diffusion, for example, would that be some combination of that?
Yeah, so if it's not Bjorken flow, then you're going to have to deal with some more elements of this C mu nu tensor. But you can construct a translation table between the general components of pi mu nu and C mu nu. You can always do it. So component by component. So for example, if this thing was diagonal, it might contain 3 anisotropy parameters, Cx, Cy, Cz. You would then evaluate the x pressure, the y pressure, and the z pressure, which would be expressed in terms of pi xx, pi yy, and pi zz. You would get 3 special functions that look like RL, but we would call them Rx, Ry, and Rz. And you would get 3 relations like this, which then would allow you to always undo the map. So yeah, in general, you can always do this. It's a good question. All right, before I do the linearization, though, I will point out the following, that just using this here, I can do a change of variables in equation 2 and rewrite it as an equation for pi, for the evolution of pi. And again, I'm going to skip over some steps because they're in an exercise which I know we're out of exercise sessions, but I'll upload it into the folder and you can take a look at it. I give you all the details about how to do the next step. So before we do the linearization, we can change variables in 2 from C to pi using our double boxed equation over here. And then you get something that on the surface is not very enlightening, but turns out to be quite wonderful. Okay, it's ugly, I admit it, but this is what it is. So everywhere up here where there's a Kc appearing, it's understood that it's a function, Kc of pi, this thing that I just drew up there, that you get from the inversion. There's a derivative hiding over here, pi bar primed of Kc. That's nothing but the derivative with respect to Kc of this relation P Kc evaluated again at using the map. So this funny thing here is just the derivative of this function, which is a function of Kc, and then I evaluate Kc at, in terms of pi. It's a funny way of writing things, but it works. And then finally, for compactness, I wrote this funny function h here. It just collects up a bunch of additional mass. Good. Good. Yeah, so there's our R function appearing again. I've just compressed this. Now, I'm sure you can understand, we knew we could do this inversion back in the day, but when we got this equation, it was so ugly that we were like, why would we want to numerically solve that thing? We could just numerically solve 2. 2 is much more beautiful. Let's stick with 2. But there's some analytic insight that we can get from 2, including the method to extract the hydro attractor comes from here. But it's admittedly not the most beautiful equation. It's like, ugly child, but you know, you still love it. All right. But once we've got it in this form, now we can do this linearization step I was advertising. Okay. So for that, we only needed knowledge of the special function I just erased, which was r, but it was 1/2 1 over 1 plus c plus tangent inverse of square root of c over square root of c. Everybody remembers that, right? Good. We're not actually going to do the Taylor expansion, but I'll just write the result. So from the plot, we saw that it was linear, right? I sketched it suggestively so at small c, and then you can even obtain the subleading term here. And Gabrielle should be paying attention now because there's a funny 21 appearing here. It's going to eventually become the 38 over 21. You can also expand this h function that's sitting here. It's just simply linear in c. And then you can invert these relations if you want, and rewrite c as 45 over 8 times pi over the energy density. Another weird number pops up. And I don't, yeah, let's write this one. Even weirder number. I'm just going to write this as pi squared, pi cubed, pi cubed. Good. Anyway. So in practice, what you need are these inversion formulas down here, and putting that together with this guy. So over here we have an h, right? So we go into h, we plug in this expression, and now we've rewritten h in terms of pi, right? Completely. This pi prime that's sitting out here, pi bar prime, I already told you what the expansion of that is down here. C, we just plug in this one here. The rest is already written in terms of pi, so I only have to attack this last bit here. And trust me, on the next step, when you plug in those expansions, where's the best place to put this? Here, sure. You get and there's the 38 over 21. So this automatically contains inside of it the DNMR result. In fact, if you wanted to work harder, you could extend all these expansions over here and get the pi squared term that's here. Work even harder, you can get the pi cubed term. Work even harder, you can get the, keep going. And each one of these terms, pi over epsilon, remember, is the inverse Reynolds number. It's proportional to the inverse Reynolds number. So in this way, you can now complete the series in inverse Reynolds number, analytically, order by order. Now, you don't have to do that. You just solve this numerically. It does it for you. There's no reason to do this complicated thing unless you want to do the proof that you have this hiding inside of there. But it's useful to convince your colleagues Any questions about the procedure I used there, or outlined at least?
Is the shear viscosity coefficients, what does it must be? It comes from the relaxation time?
Yeah, so this is, because I started with relaxation time approximation, this 38/21 is the relaxation time approximation one. If you had a different collisional kernel and you started with a hydro with a different collisional kernel, then you would get different coefficients here, but nobody's ever checked, actually, do you get the right coefficients? That's a paper to be written. It's only been checked in RTA, explicitly. But I see no reason why it wouldn't work. But that would be a very nice paper. I would immediately accept it for publication. Looking around the room, joking. Good. Now, again, skipping over lots of gory details from the ugly version up there. I guess we should call it 2 primed. And using this same change of variables that we had before, namely that we defined W bar as tau over tau EQ, and we had, phi of W was something like 1 plus 1/4 the time derivative of the log of, there's something like that, right? There's a t floating around here. Something like that. You can map this equation to an attractor equation just like we did with the DNMR equation. Where, wherever there's a QC, it now becomes QC is a function of phi instead of pi. But you can write it down, and amazingly, it's actually more beautiful, and I don't really understand the reason why, than that thing over there. There must be an underlying reason, but I never understood. Where now QC in this equation is understood as QC is a function of the Heller and Spolensky phi variable. Anyway, I think going back in the notes, you can figure out how to rewrite this. So this is now the attractor equation. Now, unsurprisingly, if you Taylor expand this attractor equation to, to order phi squared, you get exactly the DNMR attractor equation that we wrote down a couple of days ago. But you can expand it to higher orders if you like, and you'll get different attractors that are better. The other thing you can do is just solve this thing numerically. Now remember, our way to find the boundary condition for the attractor equation was that we required that that term goes to 0 when omega bar goes to 0. So we see that just makes the left-hand side of this equation go to 0, and then, well, this is never 0, so you just have to solve some nonlinear equation related to the stuff in square brackets there. And you'll find in practice that there's only one solution, and analytically, its phi is 3/4. And now I have to reconstruct the equation. So PL over PT was this, so 3/4 saturates the bound on the tops. That guarantees that this never goes negative. And so this point corresponds to PL 0 is 0. So written in this way, we see that the for the anisotropic hydrodynamics equations, the boundary condition for PL when omega bar goes to 0 is simply 0. And some people were asking me, like, because they're numerically solving the attractor equations and RTA and stuff, why is this the right boundary condition to use? Well, that's because in very early times, you're dominated by the free streaming term. And ahydro incorporates the free streaming term exactly, and it's telling you this is the right boundary condition to use. So, good.
Sorry, now 5 + 1.
I don't know if I remembered that formula correctly. Does anybody have the notes? I don't know if I got the bottom right. -1, +1, I don't remember anymore. I think it's -1. No. Somebody look it up so we get it right, because my memory's. -1, yeah, sorry. Is -1 down here? Okay. Yeah, I mean, the important part for this relationship is the top. Like, if phi ever becomes bigger than 3/4, which it did in DNMR, it does in MIS, in Mueller, Israel, Stewart, it does in BRIS, then PL goes negative. In this case, it never does, it's bounded. And that's related to the fact that the inverse Reynolds number is bounded and all those other things that are wonderful in life. Yes?
When you solve the attractor equation,
Yeah?
you also know the corresponding subspace of the initial state that will eventually converge to the.
Yeah, so this just tells you the boundary condition, but then then this thing is horribly nonlinear. You have to solve this ordinary differential equation up here as a function of log omega bar and it has this exact solution that it saturates the upper bound, and then it goes to equilibrium, not slightly below equilibrium, to equilibrium. So you can solve it exactly. You know that it goes to equilibrium. Is that your question?
The initial state, so the now the difference initial state that will converge to the contractor.
Yes.
But only a subset of the phase space that the initial state resides in.
Yeah, all I can say, yeah, there might be solutions, and I never checked for them, outside of this physical region, because this is the physical region. And I can tell you that any solution that starts in between 2/3 and 3/4 converges to the attractor. The ones that start out here with negative pressures, they may run away. I've never checked it, because to get a negative pressure in this, you would have to have a complex anisotropy parameter. It would be really weird. It's very hard to do. I never checked it. Yeah, but within here, all solutions converge to that attractor. Good. All right, I gave you various selling points for why it's better. Inverse resums all orders in inverse Reynolds number. It has the right limit for the attractor. But then the question always is, how do you know it's better, right? You need some way to test something in physics. So a few years ago, together with my collaborators in Krakow, Wojciech Wlorkowski and Radek Wróblewski, we decided it would be good to have such a solution that was, simple enough that people could start comparing their various hydro approximations to, and then you would be able to say which is better and maybe improve your model, right? Because if we're always comparing to data and data has error bars, then we're all just going to be arguing with each other forever. We need some, really objective way to say what's better. And that's provided by exact solutions. Now, since the first exact solution, which is the one that I'm going to sketch today, there's been other ones. This is the exact solution for RTA in Bjorken flow. Conformal. Now, the same method can be applied to non-conformal Bjorken flow and also conformal Gupser flow, if anybody knows what Gupser flow is, and get an exact solution. Gupser flow is quite interesting because it doesn't just have longitudinal expansion, it also has transverse expansion built in. It's a funny thing that this guy, Steve Gupser and collaborators found. That's a sort of generalization of Bjorken flow that also allows for transverse expansion. And in a funny coordinate system, which doesn't have a nice name like Milne, it maps to a static flow. But then in general, it's this really weird thing. Anyway, we'll focus on the simple case, conformal Bjorken flow. And we've seen this equation before. It's the Boltzmann equation in relaxation time approximation. And it's conformal. We know what the relaxation time is. It's that thing there. Now, I'm going to make an additional assumption for the derivation today. You can go beyond this. I'm going to assume that the equilibrium distribution function for our problem is just a classical Boltzmann gas. So no Bose distribution or Fermi-Dirac distribution. But there are papers where this, with my name on it, where this has been extended to include those cases as well. But this will keep what are going to be some big formulas smaller. So let's do that. So how do we solve this thing exactly? In preparation for my lecture over Christmas, my daughter and I were playing with ChatGPT, and I asked it how to do it, and it didn't know. Didn't know. But it did write a Python code that would solve it numerically, which was amazing. I didn't actually run the code because I was afraid that it had a virus or something. You can't trust those AI. Good. So I'm going to introduce some boost invariant variables, and I was going to try to write the Polish names associated with it, but my Polish spelling is Chiz, C-Y-Z. I have no idea how you spell his name. Anyway, so Polish guys back in the late 80s, early 90s, introduced this set of variables. And I apologize, it's another W. But I'm gonna try to always write it with little angles to distinguish it from our dimensionless time variable we've been using up there. Two variables I'm going to introduce. Are these two guys. So if you, these things are manifestly boost invariant. If you boost both the momentum and the space-time variables appropriately, you'll find that they're completely unaffected by boosts. So they're a good starting point for a boost invariant problem. We can rewrite, by inverting these relationships, the energy and PZ. Sorry for the squeak. So, and in addition, because we're in kinetic theory, we're probably going to need to rewrite the invariant phase space measure. So I'll go through, this was just algebra, so I won't show you the steps there, but here I'll show you some steps. So the invariant phase space measure I can write is dpz over 2 pi cubed times over the energy times the transverse guys. And now I want to replace dpz by dw in the end. So from there, I can just evaluate that from here. And from the second relation down here, I have that dv is nothing but w dw over v itself. So I plug that in there. And then I can rewrite that equation in the following way, and then I recognize that what's sitting here in the parentheses was nothing but tau squared times the energy in the first place. So as a result, dpz can be written as E to EW over V. And that means up here that this is simply all right, so I've just replaced my PZ integrations now by integrations over this boost invariant variable W. Turns out it will become useful for solving the RTA-Boltzmann equation. And yeah. There was supposed to be an exercise associated with this, so now I'm going to feel guilty doing the next step. Maybe we can do an extra exercise session in the afternoon to cover the next step, but I don't want to get bogged down in the next step. So if you carefully go through this equation, you start expanding things out, right? So what's sitting over here is E times a time derivative plus PZ times a Z derivative. And on the right hand side, this is just going to be E. And then you carefully change variables to W and V. We'll do an extra session this afternoon to do this because it's not exactly trivial. What you'll find is that this equation here, when rewritten in these funny variables, simply becomes d tau of f is minus 1 over tau eq, f minus f eq. And I'm going to leave that tau eq can depend on time down there, just to make it non-trivial. If it didn't depend on time, actually, we would know how to immediately solve this equation. It's just an exponential. You're done. You solved the RTA-Boltzmann equation. Now, in general, tau eq can depend on time, remember, because the temperature depends on time. So then you need to be a little bit careful about the next step to solve this guy. But this looks a lot simpler than, having two derivatives flying over here. You just have a proper time derivative now. And you can solve it exactly. Okay, that turns out to be the solution. And you can explicitly verify it. It's one of the exercises where, yeah, if we don't have time to go through it explicitly, I'll just post the solution in the folder. If you want to verify that this is actually a solution without knowing how to get it in the first place. You can just take this and plug it in here and simplify it, and you'll find that it is a solution. So trust me, it is a solution. Now, I've been very careful because it's important when you're dealing with this thing that, this is a tau primed integration, and down here, tau EQ depends on tau prime, and FEQ, because the temperature depends on time, also depends on tau prime there. And then here, I was very careful to call this tau double prime, because you can easily get confused which is the time variable floating around in this thing. The first term that's sitting here, well, let's look at some limits. So again, if tau EQ goes to infinity, we should go back to the free streaming limit. That's this first term here. If you work it out, we'll look at it explicitly. You get the free streaming limit from this first term here. And this other term is the equilibrating part. Now, I suppressed some variables here, but in general, right, this thing also depends on W and PT. So maybe we should put that back. And everything on the right-hand side also depends on W and PT. So you could, in principle, now solve a two-dimensional integral equation in a grid, and then you could get an exact solution for the evolution of the one-particle distribution function. But it turns out that there's an easier way to solve it, where you can reduce it to a one-dimensional integral equation. And I'll try to sketch the steps. I won't go through all the gory details, but just sketch the steps. But the basic idea is that, remember up here, why did I rewrite this invariant phase space measure? Well, I use this when I want to calculate things like the energy density, right? So what I'm going to do is take a moment of this distribution, of this equation here. On the left and the right, I'm going to multiply by P naught squared, the energy squared. Then I'm going to integrate over all momentum using this invariant phase space measure. And then I'll get explicitly on the left-hand side by construction, that will just be the time-dependent energy density. This will turn out to be the free streaming contribution to the energy density. And there'll be another equilibrium energy density looking thing hiding under here. So I can reduce it down by taking a moment of this equation, the first moment in my old hydro language, and then I can get an integral equation for the energy density, which is a scalar one-dimensional function of proper time, and I just solve it as a proper time, as a function of proper time. So, how does that go about? Well, first, we need to write what is this funny function that's sitting over here. Again, it still depends on W and PT. Let's see how that works out. So it's just because we assumed a Boltzmann distribution, that's our equilibrium distribution for this example. And just a second. It turns out that this, and I'm even myself not remembering what the step is there, you can write that completely in terms of the v variable. Right, yeah. So in a general reference frame, right, this is not necessarily the local reference frame. This is just E dot U over tau. And then you can use this second relation. Oops, that's in the square root. So right, our thermal distribution function. So this is what's sitting out under here when written in terms of the W variable. It still has PT dependence. It depends non-trivially on the proper time. Now we can simplify this a little bit further by using these basis vectors that I introduced earlier. I remember I had introduced some basis vector z mu, otherwise known as x3 mu, that was the space-like Cartesian basis vector. In a general frame, where eta is the rapidity now, that vector looks like this for a boost invariant system. In the local reference frame where eta is 0, this is our old Cartesian 0, 0, 0, 1 vector. But in a general frame, it becomes this form. It's just a boosted Cartesian guy. And remember, u dotted into z is 0. And if you work it out, p, the forward momentum dotted into this z vector is nothing but that w variable divided by t. And in fact, this is the way to see that this thing is Lorentz invariant, because you can express it as this Lorentz invariant contraction between these two 4 vectors. So this thing is the same in any frame. It's just forward momentum dotted into this space-like vector. So using that, we can rewrite FEQ above as e to the minus square root pt squared plus pz squared tau over tau prime quantity squared divided by the temperature at time t. Now the reason I wrote it back out from the w and the z variables is to emphasize a point. Well, one, this thing has some non-trivial t, and let's assume we're holding t constant and we're varying d primed. It has some although it says FEQ, it is a deformed FEQ. And in fact, if you look at it, it's in a hydro form. It's this deformed ellipse thing. So once you know how to do ahydro integrals, you know how to do integrals involving this beast. So that trick that I taught you last time is how you take the moment on the right-hand side over there. You factorize the angular parts of the integrals and then you just do them. So because this thing is actually already in ahydro form for you. It's P dot Z. You should think of it as P dot Z, but I just write it as P sub Z. Yeah, This is really Lorentz invariant P dot Z. Good. And then I'll write down 2 more things and then we'll take a break. Yes?
So you can compare this IQ with the one on the top bar, that's the Boltzmann. On the top bar. On the top bar, there is also an FEQ.
Yes?
So the bar above.
Up there.
Yes. So you said that the difference is to the specific U. Could I understand it this way? If I compare these two?
If I compare this to, I mean, so this is still, yeah, it's this funny way of changing these variables to these W's that introduces this square root, and yeah. It's equivalent to the Boltzmann distribution. Of course, in the limit that tau goes to tau primed, this just reduces to a Boltzmann distribution. But when it's this deformed Boltzmann distribution, yeah, it comes from this P dot U when written in these funny coordinates.
Could I also think the specific form of U and the specific reference frame? So
Yeah, you can think about it that way. Because, I mean, this P dot U thing, if you work it out, is just this V that's sitting here up to a factor of tau primed,
in some parts
up to a factor of tau.
you choose the local reference frame. So but for your result, you do not have any frame dependence.
No, we don't have any frame dependence here. So here, everything is completely frame dependent. I'm being careful to make sure that it's written in a frame independent way. But this thing, and I forgot to write down the relation, there's, you can write this variable V as well in terms of P dot U, and P dot U is just V over tau. And then there, you might think that it looks nice and linear here, but then you can rewrite it because there's a relation between these two things, and then this funny square root pops up. But yeah, this is manifestly Lorentz invariant. That's manifestly Lorentz invariant. I've tried not to pick a frame on purpose. Lorentz frame. Now, so with this knowledge, you can plug that in there. And now if I were to integrate on the left and the right, all integrals over W and V, or if you like to write them as PZ, PT integrals, they just attack this part. And they give an energy density, essentially, that's going to depend on tau and tau prime. And I'll write it down explicitly what it looks like in the end. We also have to choose an initial condition here. And of course, you could choose whatever initial condition you like. I'm going to choose my favorite initial condition, which is a deformed spheroid, because it's simple to deal with and I can do the integral. So I'm going to choose this to be a Romachka-Strickland deformed spheroid. So I'm just going to squish it by some factor in the z direction. So we're going to use this board. And then I'm just going to write down the answer and then we'll break. So when all the dust settles, and I can provide notes to everyone to show all the dust. I've shared them with one person in the class already, so I'm happy to share them with everyone. And I don't know if I would bother writing down this equation in your notes because it's important, but it's not one that you need to memorize. You can just go look it up in a paper. All right. So there's a bunch of integrals which you have to do, which I won't bore you with. I can, as I said, provide you the details in some notes. There's some special functions popping up here. So it was originally an integral equation for the energy density, but because it's a conformal system, energy density is always proportional to t to the fourth. So I can get rid of that constant in every term and just write it as a formula for t to the fourth. There's some special functions flying up. This h20, it's just another way of writing this r of Cassey function, as it turns out. But it depends on some new parameters, which we call alpha, which are just the square root of 1. They're related to Cassey in this way. That's a Cassey. It was just more beautiful to write it in terms of these guys, especially when you want to generalize this equation. All right, so what do you do with it? I'll say what we do with it, and then we'll take a break, and then I'll show you actual solutions to this equation and comparisons of various hydro schemes to it. So what is that? So this is some integral equation, and the way I can solve it is the following. Let's say I don't know what t of tau is. Let's say I just assume to begin with that it's the Bjorken solution. So I just, in my computer, I put 1 over tau to the 1/3. I plug that in and over here on the right-hand side. I numerically do this integral between t and tau naught and t. I add it to this term. I get a new t to the 4. I then do it again. And I just keep doing that until it converges to some answer. And luckily it converges. You could be in bad luck that doing that procedure doesn't converge all the time. It seems to converge no matter what initial condition you throw at it. Of course, you can make it converge faster to the solution by a more clever initial condition, but in practice, I just choose the ideal solution, and then just within a few 10 to 100 iterations, it's converged. Now, what do you do with that once you have it? Well, once you know t as a function of time, then you know this FEQ as well, sitting over here. Because this was an unknown. We didn't know what that was, but now we do because we solved the integral equation. We can now plug that in here, do this integral, add the initial condition piece, and now we have the full solution of the one-particle distribution function in all phase space. So by solving one one-dimensional integral equation, you can solve the entire RTA-Boltzmann equation. Good. I think we all need a break. Sorry for going so long. Let's come back in 10 minutes. Is that okay? Check, check. All right, we're in the home stretch. Great. So now just do a kind of wrap up and show you some comparisons between, because it's hard to plot, exact solutions on the board. I can sketch them, but maybe you won't believe me. So I had prepared some slides, and we have a little bit of a review going back to the slides that I presented on Monday already. But now, hopefully, you're in a much better position to understand what's actually being plotted here. At least in some special cases, we learned how to extract this black line. And today, we even derived, in sketchy form, the ahydro attractor equation. And we showed that it had a fixed point at PL of 0 when omega bar goes to 0 over here. And that we have all these solutions that converge. So these are actual numerical solutions. In the dotted cases, I just solved those two ordinary differential equations, one for lambda, one for C, varied the initial condition, and in this one I just solved this guy here and put it on the same plot. Yes?
So we did just for finding attractor from that differential equation, you just found the initial condition, you didn't find the asymptotic series, right?
No, well, from here you can find the initial condition by simply setting this to 0, and then the stuff in the square brackets has to vanish. That tells you the initial value for phi when omega bar goes to 0, but then you solve this numerically with that boundary condition, and that gives you the black line.
But you didn't do the total bar just to see how this little expansion to see how
Oh yeah, I'll show you that. So yeah, you can also expand this, and I'll show you that in a few slides. You'll be interested in seeing it. Yeah. Yeah. Sorry, I didn't understand the question.
So a numerical solution of the array of light as in the Hydrodynamization equation of the solution of what we think which set up that is a topic I really
Yeah, so I used the equations that were on the board about 30 minutes ago. The one that said, you know, the d mu t mu nu is 0, and that equation for QC. I just solved those two together. I had turned them into an equation for evolution of lambda and QC. That's what the gray dashed lines are. And then I choose a bunch of different initial conditions, and this was the solution to that special equation. Good. Yeah, so PL over PT is going to 0. I mean, omega bar to 0 is way over here. But if, so what's your question here? Sorry.
So you said that if the limit omega bar goes to 0, we will have a solution like phi is 3/4.
Yes.
And at that point, the ratio to the other PT should go to 0.
Yes.
So
Well, how do you, I mean, so you can't read phi off of this plot. I mean, phi of 3/4 is PL of 0, so yeah, it's way over there. It's off the plot. I can't. 0, yeah, if I kept going, it's over there, like by the Domo, I think, if I got it right. Yeah, then that would be 0. I just, I truncated it there for purposes of presentation. Good. And we saw this slide before and a different version of this in Bruno's talk yesterday, as I recall. This exists in a variety of different theories. We discussed the exact solution today and in this language, if it ever goes above, I think there's minus 2/3 or something. He uses a different variable here. If this goes above this tick, you have a problem and you generated a negative pressure. You'll notice that the exact RTA solution, the ADS solution, both obey this bound, whereas viscous hydro violated it. So it exists in a lot of different theories. You know, of course, let's focus our attention on these, which are, you know, our prototypical kinetic theory example and our prototypical strongly coupled example. We see that after some amount of time, the solutions become universal. And if I were to put these on the same plot and rescale by the corresponding relaxation time, instead of plotting it as just tau t, these guys would exactly collapse onto one another. It wouldn't matter if I was doing kinetic theory or ADS CFT. They're the same. But what does change is this early time behavior, right? So what this tells us is this late part of this attractor business is universal. It's independent of the microscopic model you're using. And by the time you hit that universal regime, typically you're already in the Navier-Stokes limit, and you can write down nice analytic solutions. Now, there's a bit of no man's land where people don't know if it's universal, non-universal, how much it varies in between these two orange lines. But over here, it's clearly non-universal. The behavior that I get down here dramatically depends on the microscopic model that I have. But we know that whatever happens down here, it eventually has to emerge onto this line up here. So that removes a lot of uncertainty from the game. Now, universality is good. All microscopic theories are equally good starting point. Just pick the one that's easiest for you to use. You like kinetic theory? Use kinetic theory. You like ADS-CFT? Use ADS-CFT. If you're only interested in equations at those late times, doesn't matter. Non-universality, though, is important as well. You have to pick the microscopic theory that best describes the system's dynamics. And I would argue that at the very earliest times after a heavy ion collision, when the temperatures are the highest and the coupling constant is the weakest, that's when it makes sense to use kinetic theory, of course. It doesn't make sense to have a strongly coupled theory there. But, you know, we can debate. In addition, the other place where we saw things going haywire was on the edge of the plasma, where things were dilute, and it's also not strongly coupled there. It's weakly coupled. Again, kinetic theory is the best thing there. So this is my push for kinetic theory as being the way to go, because you're guaranteed, if you choose your parameters right, you're going to match smoothly right onto this curve, just like everybody else does. But you're getting the physics right in this phrase. You can match onto the CGC in a self-consistent way. You don't have to fiddle around with extra dimensions. And we went through the steps of how to get the attractor. I'll leave these slides up only briefly. We went through it on the board. We can transform these equations using some dimensionless variables, and then we can get some nice looking ordinary differential equation, which we can then solve. And then we can find the boundary condition, and then we numerically solve it. Great. Now, all of this stuff about the exact solution was sort of setting up the next set of slides, which is, can we go beyond hydrodynamics in this attractor business? We showed how to get it in the ahydro case, and we showed how to get it in the viscous hydro case, right, analytically. But that, for hydro, it's always dealing with a reduced set of degrees of freedom. Only in the Bjorken case, there's only 2 degrees of freedom floating around, right? So there's surely more degrees of freedom hiding out there. And if we went to the full hydro theories, right, there's only 14 degrees of freedom. But a kinetic theory has an infinite number of degrees of freedom because it has the full momentum dependence of all of the particle distribution functions. And we describe it through, some space-time dependent one particle distribution function. Now, the things that we've been looking at so far, like PL over PT, oh, it has an attractor, we're great. Those are all based on T mu nu. It's a very low order moment of the one particle distribution function. What would happen if we start putting more powers of P in here, right? Well, what happens in practice is that this integral becomes more sensitive to the high momentum part of this one particle distribution function. The fewer powers of P over here, more I'm dominated by the low momentum part because this thing is rapidly falling in momentum space. So we might want to look at higher moments of the one particle distribution function to see what high momentum modes are doing. And that will go beyond hydrodynamics. And for that, we saw in one of the student talks yesterday this set of moments that I introduced in, I don't remember, 2017. I mean, there are more complicated ways of writing these moments. Gabrielle and the hydro people, they have a different version of these things, which has some special properties, but I was trying to get to the simplest version that I could explain things to people with and use. And it's the following. So I can introduce as many powers of the energy down here and as many powers of PZ in this integral. Now, I'm specializing to the case of Bjorken expansion. You might ask, why can't I put powers of PT in there? Well, they're on-shell quasi-particles. So anywhere I have a PT squared, for example, I can always replace PT squared by E squared minus PZ squared, and I can rewrite it into one of these moments. So these actually form a complete set for the Bjorken expansion case. And it doesn't matter if it's conformal or non-conformal. For on-shell quasi-particles, these are a complete set. Now, I warn you that not all of them are completely independent. So some of these have relations to others. So you need to be a little bit careful drawing conclusions when they do have a relationship. But they're nice. Now, the reason there's a 2p here is because in this theory, the one particle distribution function is always an even function. And so any odd power of pz here will integrate to 0. And so we don't even talk about them. If we look at M20, it's nothing but the energy density. If we look at M01, it's nothing but the longitudinal pressure. M00 is the number density. But then the rest of them, they don't have an analog. They're not hydrodynamically named, let's call it. So on the board, we went through this, in sketch form again. How do you go from the RTA-Boltzmann equation to some integral equation? And now you get to see them in more beautiful form than I can write on the board. And then, as I said, you can solve this thing iteratively. Once you obtain t as a function of time, you can plug in here and get the entire one particle distribution function. Alternatively, you can obtain an equation that's obeyed by any moment of the one particle distribution function. So you solve the top one. With that, you know this. You take an arbitrary moment, you get this. There's some ugly looking spherical harmonic, hypergeometric functions flying around. But computers know how to do those these days. So now you can just calculate any moment of the distribution function once you solve the top one. Done. And you don't have to iterate this guy because you already know what t is. You just write it once and you're done. You know the time dependence of this moment. You just only have to iterate once. And out of that, you can get the solution in this exact RTA case. And what I've plotted here is the exact solution is this in here for our Hellerens-Belinsky phi variable. As we can see the exact solution saturating this 3/4 up here. And if you look carefully at late times, it's going to go to 2/3. I chopped that part of the plot off. You'll see it on the next slide. And then on this plot, I plot what the Navier-Stokes solution is. Mueller, Israel, Stewart is the blue line. DNMR is the red line. And then sitting there in the black is A hydro. So as I advertised, by eye, it's indistinguishable. Now, in the paper, we took the ratio of those two curves, and you can see there's like a 0.001% or something deviation. Now, this is a coincidence. I mean, it's not a complete coincidence, but it's not guaranteed that this works as well for all moments. Now, Gabrielle asked, what happens if you take that A hydro thing and you don't solve it exactly, but you just extend it to third order? In this case, I extended it to order phi cubed. And then you can analytically calculate this equation. You get a new attractor equation, and you can put it on this same plot. And as you can see, it gets you almost to the exact solution. And here, I'm just using A hydro as the stand-in for the exact solution because it's indistinguishable from it in this plot. You can go to phi 4 and make it even better. But why would you do that? You can just solve two ordinary differential equations in Mathematica. Maybe even your phone can do it. All right, so what happens to the other moments? So as I said, after you solve that integral equation on the top, you can plug it into that big boxed equation on the bottom and get all moments. And in this plot from 2018, I just varied the initial conditions around, and what I saw was that every single moment collapsed. It wasn't just the hydrodynamic degrees of freedom, it was every moment of the one particle distribution function collapsed. And what that told me immediately was that, well, at least within RTA and the set of assumptions that I had made, that there was an attractor for the entire one particle distribution function, that it was beyond hydrodynamics. And trust me, I went even further down in the panels, but till they became stamp-sized. And you can extract from that solution, as I said, plugging the iterative solution into here, you can extract what the actual attractor for the one particle distribution function looks like. And if you're trying to solve the Boltzmann equation numerically, in some momentum grid, you're going to have a hard time describing this feature of it, which is that you have basically a delta function sitting here at pz is equal to 0. This is the free streaming term. Now, as a function of time, that feature becomes less and less pronounced. That's because this damping function goes to 0 when tau goes to infinity exponentially, and it turns off the free streaming part, and the other part takes over. And then you can compare just an arbitrary initial condition, how does it evolve, and you can see that it's going towards this sort of universal form of the one particle distribution function. Now, I won't go through these slides, but you can make various slices in space to try to simplify it from that 2D picture down to 1D pictures, and you can see the attractors very much easier that way. So the other thing I advertised that the exact solution was going to be able to do would be allow us to assess different hydro schemes. Well, we already saw that for PL over PT. Now we can look at all moments of the one particle distribution function. So this is PL over PT. It's actually just PL over the PL over PEQ. There's an ahydro line on top of this black line. You can't see it. They're basically identical. This is the Navier-Stokes, and this is viscous hydro DNMR version. And then over here are the 0 moments. You can see that there's ahydros not doing so great over here. All the hydro approximations all sit at 1, so they're even worse by some measure. And then as we go down to the right, we see that the hydro approximations for higher momentum modes start to break at larger and larger W bars. So if I try to go back earlier in time, they break earlier. So down here, they're not going to get this high momentum part of the distribution function right. Ahydro is also struggling a bit, even though it was based on RTA. And the reason for that, I'll come to in a slide, if I don't pull my headphone off, is because of this feature that we see in the kinetic theory solution. This doesn't look like an ellipse, right? And it doesn't look like a spheroid. It looks like two spheroids. It looks like some free streaming spheroid and then some equilibrating spheroid outside of it. So if you try to just describe that by a single deformed thing, it's not going to work perfectly. So that led us to say, can we do better than this? So now we're going to take our inspiration from the fact that this exact solution always has a free streaming piece and a not free streaming piece. Now, if you're doing kinetic theory simulations, this population of particles, the free streaming ones, are the ones in your simulation that, although you were Monte Carlo sampling collisions all the time, they never underwent a collision. They're the free streaming part of the population. And it always exists, you know, there's some small subpopulation of them. Yes?
Speaking from this point of view, how you look at the corona models, the corona models that
Yeah. Yeah, so there was all this stuff in the press recently about, you know, how some people in, I think, Sofia University, Hirano and company had solved, you know, a key problem in quark flow and plasma physics. I think A-Hydro already solved this problem by already having the free streaming limit right on the transverse edge, but I don't.
So it's already included in
I think it's included in A-Hydro. I don't think it's included in other.
because there are other approaches with the simulators, event generators, which you really have the two components.
Yeah, in A-Hydro, we don't have to have, that was one of the goals, was that you didn't have to have a two-component thing. You can run in the dilute regime.
No, but
Yeah.
because it seems that you have hydro doesn't work because you don't have the corona part with free streaming, and
Yeah.
then you have to add this is,
Yeah.
like,
Yeah, that's my opinion.
you're
But I wasn't going to say anything, but you prompted me. Yeah, let's suffice to say Google News upsets me sometimes. All right. Yeah, so the idea was to try to incorporate a sort of two-component model. This was a work that I did with my Kent State graduate student, Huda Alalawi, a couple of years ago during COVID. We did it all remotely. And there, the idea was that we take a free streaming form here for the first term, multiplied by one of these damping functions like we had out of the exact solution, and then this normal A-Hydro ansatz over here multiplied by 1 minus the damping function. And the idea being that at early times, you know, you'll be dominated by this guy because damping function is 1 at early times, and at late times you'll be dominated by this guy because damping function is 0 at late times. And you can just take this ansatz and then work through the same sort of machinery that I was showing you here in the lectures. You can derive a set of coupled ordinary differential equations, the first moment of the Boltzmann equation, second moment of the Boltzmann equation. This one looks eerily similar, right, to the one that we saw, except for there's this 1 minus d thing hanging out here now. But it's basically the same equation. And now you solve these two numerically. And this is what we found. Now this is now a log scale here, so you can compare things better. But remember, A-Hydro wasn't doing so hot on these low momentum modes, but now once you add this free streaming bit in, you can do a lot better. So there, you know, this is an advertisement not for, you know, my particular method of solving this problem, but the method of using exact solutions to guide your thinking. Now, of course, everything that we did here was with conformal symmetry for simplicity. But in general, life is not conformal, right? So what happens when you break the conformal symmetry? So we went through this derivation in the non-conformal case. Eva Maksomiak from Kielce/Krakow, mostly Kielce in Poland, and Wojciech Flarkowski, Radek Lublewski, and myself in 2014. In that paper, for simplicity, we took a constant relaxation time because it was numerically hard to do. And we were able to write down the integral equation that would be obeyed by, in this case, a classical massive gas. So that's where these Bessel functions are coming from. This is simply that integral equation for the energy density. This is just the energy density of our massive gas on the left, and this is that same stuff from the right, now with an extra parameter floating around, which is the mass. And what Huda and I did at the end of last year was to extend the solutions of this equation, because we had already written down the equation, to the case that tau EQ can depend on both the temperature and the mass. So now tau EQ is a fully non-conformal thing. It's no longer simply inversely proportional to t. And so remember, a lot of these plots, we can say, oh, it's just tau t, t is the only scale, and that's the reason everything collapses. So many people would argue, when we would show these things, and it was a good argument, well, what if you had another scale in the problem? Is it still going to collapse? How would you choose the rescaling thing? So our assumption was that we could just take the now temperature and mass dependent relaxation time. It's plotted here. There's some complicated analytic function. You can compute it. In the limit that m hat goes to 0, it reduces to the conformal case. But as you go to larger and larger m, the relaxation time increases. So it should equilibrate more slowly. But you can solve this integral equation numerically, and then what you find is this, that if you just rescale it by now this non-conformal relaxation time, you find by and large, and let's focus on first on this large set of panels, that as I vary the initial conditions, all the moments seem to collapse again. So once again, at the level of the hydrodynamic descriptions, which are this panel, and then all of the one-particle distribution function, it seems to be collapsing. Now, there were some exceptions, though, in these moments that are sitting down here. And those are the ones that are most sensitive to that free streaming part of the distribution function. And as you can see, there doesn't appear to be convergence at very early times here. There's a little bit of spread, but there is a late time attractor. You can see that they somehow do eventually collapse onto a line, but there's doesn't appear to be an early time attractor. To check that carefully, what we did was keep the initial conditions constant and then vary the initialization time. And then you can see that, in all of the ones in this sector, they all collapse. Now, there's some hydro curves on here. One is, they're both second-order viscous hydro predictions in the 14-moment approximation and Chapman and Skog approximation, but first order. Now, over here, you can see that there doesn't seem to be an early time attractor. They're not really falling onto some sort of universal curve here. And this is what the black line is, what we identified as the attractor. But these other solutions only approach it very slowly. So in this case, we can say that there's some subset of the moments that seem to exhibit an attractor, but not all of them. And this is in particular some very low momentum part of the distribution functions. From that, you can rewrite the bulk viscosity in terms of those moments. And primarily, there's some normalization that just comes from P down here, but primarily it's that M00, which was the upper left-hand panel of all those plots. And that's what's shown below down here. Wait a minute, yeah. What is shown here? Oh, I show them all. Yeah, so this is everything, varying the mass, and then this is varying the initial time, this is varying the initial condition. And you see that, there's a little bit more spread in these variables, the shear viscous correction and the bulk viscous correction. But, they all do collapse at late times. And although there's a bigger deviation in the bulk correction is always so much smaller than the shear viscous correction. You can ask, does it really matter? I don't know. So anyway, it's an open topic of discussion. So now I'm going to go back in time, another 2 years. So RTA is great. It's very simple, right? It's not really QCD. It's great that you can get exact solutions. It's great that you can compare different models to it because you have an exact solution. But then the question became like, well, what actually happens in QCD? So there were indications from earlier papers from Keegan, Romachka, Schlichting, Kirkala et al. that at least for the PL over PT ratio, QCD, if you numerically solve the effective kinetic theory equations of motion based on Arnold, Mori, and Yaffe effective kinetic theory, that there was an attractor for that. But nobody had ever looked at the higher order moments, so that's what my student Dekrayat Almalal and myself and Alexei Kirkala did in 2020. And we just wanted to regenerate, this plot that you get from RTA, you vary the initial condition, what does it look like? Do it in QCD. And here we chose two different kinds of initial conditions. One is this spheroidal Strickland deformation, and the other was a CGC kind of deformation. And it just had different momentum dependence. They were still squished along momentum in momentum space, but this one had a different initial momentum profile than this one. And as you can see, they converge, right, after some very quick amount of time. This is still conform. This is pure glue, so it's just gluodynamics here. It's in the boost invariant limit, so you can try to relax all of those assumptions, but at least in that case, it seems to exist. Since then, people have also included quarks in the simulation, massless ones, and it also seems to work. You can also look at the pullback attractor in this case. So what happens at early times if you just keep the initial conditions and do it? Now here there's a little bit of blur. I'm not too upset about blur. Other people are like, oh, it's not exactly a line. Well, this is a very bad, hard numeric problem to solve where I don't know if you saw the grid sizes we had to use. We had to use a 250 by 2000 grid in order to even get these solutions out. And I'm pretty sure if we had worked harder numerically, we probably could have gotten these to collapse down to a line. And then you can compare to the various attractors that we've derived here. So the Navier-Stokes attractor, the DNMR attractor, the A-hydro attractor, and we can see that, well, QCD has a different one. Not surprising, right? It's none of those things. This is RTA attractor essentially, right? So what we see is that there's a different attractor, but that's not, necessarily a bad thing. The only thing we want to say is that there is an attractor. And if you look at all of the moments, you see that, and now this is varying initial conditions and initialization times in all of those guys. And if you just squint your eyes, you can see the line, right? You could probably extend it with your eye. If I gave my daughter, she could draw the line that's supposed to be there. So this is evidence that there's an early time attractor and a late time attractor in QCD, and that it's distinct from the hydrodynamic attractor. Hydrodynamic attractor only kicks in at later times, but we seem to be able to extend this attractor back to very early times. And it's non-hydro, but it's a non-equilibrium, non-hydro attractor. So I think that's why they let us into PRL. Here's a zoom in case you didn't want to. Okay, so the other thing that we did in this paper was to look at this question of freeze out, because now we had a numerical solution of the kinetic equations. We could then test different freeze out prescriptions. So this is what freeze out looks like in reality. It's actually a 3D hypersurface. These are different proper times, and then there's some coding here. And on the color coding, which are indicating some parameters on the hypersurface. But then what you're supposed to do is use some ansatz, right? Remember, I have to take F plus delta F. There's a standard one that everybody typically uses in the literature is this quadratic ansatz, and I've cooked it down to just the Bjorken case, where you can write it simply in that form we derived on the board the other day, p squared minus 3pz squared. I wrote it a couple of days ago. That's supposed to say V hydro, sorry. Oh, V hydro, sorry. There's another one that if you actually try to derive this thing by carefully taking moments of of the Boltzmann equation in this Amy theory, you'll find that there's a Landau-Pomeranchuk-Migdal effect that instead of getting p squared here, you get something that's closer to p to the 3/2. It's actually p to the 1.38 if you ask Guy Moore for the exact answer, but for us, this was close enough to test it. And then the third thing we tested was what we use in A-hydro. Because in A-hydro, we don't ever make this linearization. What we do is we assume that all times in the simulation, it can always be written in this form. And then we just have to extract the anisotropy parameters and then feed it into this thing and then sample from a distribution function that's always positive. Yeah? So it never breaks. You never get negative pressures. You never get violation of positivity. So, question is which one's better? Well, I liked the answer because the answer was that if you take these three ansatzes and you fix so that they all on the freeze out hypersurface at so we're now freezing out at different proper times, which correspond in Bjorken also to different temperatures. And at this, we made sure that all theories had the exact transverse and longitudinal pressure that they're supposed to have. These are all the same. And then you can look at higher order moments and say, well, how well do these different forms then predict the time evolution of the other ones? And you find that there's a ranking. Blue is the quadratic one, green is the LPM improved one, and red is A-hydro. So of course I was happy when I saw that. And we made, if you're interested, you can go and look in the paper. There's, giant multi-panel displays showing that this works for all moments. So another way that you can use these, kind of solutions to test things. Good. I think I'll end there. I think it's a good time. I'm right on time, sort of, within a minute or less. No, I'm over. Damn. I'm over by 15 minutes. Sorry. Somebody should have spoke up. Thank you for your time and your attention. I hope you enjoyed it. All right, 10 minutes. Sorry.